Lesson 8.2. Welcome back. Some of us forgot what we learned before spring break, so let me refresh your memory. Arithmetic mean is a fancy way of saying like find the average, so you add the numbers together and divide by how many numbers there are. Geometric mean is the square root of the product of the numbers. So if I wanted to find the geometric mean of 12 and 50, I'd find the product of 12 and 50, which is 600, and I would square root that. Okay, and then we went over how to simplify radicals. And the perfect square that goes into 600 would be 100, so it'd be 10 root 6 would be the geometric mean. All right, same thing for number 2. Geometric mean is the square root of the product. 24 times 45 is 1,080. Woof, that's a big number. Did anybody find the perfect square that went into that? Matthew?
36.
It is 36. Good job. So the square root of 36 is 6, and it's 36 times 30, so 6 root 30. Good. All right, so there's a refresher of geometric mean, and the reason why we have to know how to do that is because there's 2 big theorems we talked about with right triangles that involve finding the geometric mean. Okay, the first one we talked about was that the altitude of a right triangle drawn from the right angle to the hypotenuse, so like in number 3 here, the altitude from the right angle, altitude is from the vertex perpendicular to the other side, to the hypotenuse, splits the hypotenuse into 3 segments. So in this case, 3 and 21. So the length of that altitude, this is one of the theorems we talked about, and I proved this to you with using similar triangles and scale factor stuff, is just the geometric mean of those 2 segments that it splits into. So in this case, 3 and 21. So that's 63. 9 times 7, 3 root 7. So that'd be the length of that altitude. Okay, that was one of the big theorems we learned. The altitude in a right triangle with the altitude from the right angle to the hypotenuse is the geometric mean of the 2 segments that it split into. Number 4 is very similar. The only difference here is I know the length of the altitude. The altitude is 10. We know it's still the geometric mean of the 2 segments it splits into. So it splits into 6 and x. So I'm going to write that as 6x. Okay, we did a couple like this in class because I said don't let this throw you off. Think of this as an equation with 2 layers around your variable. Anyone remember what we do next? Square both sides. Good. Square both sides because that gets rid of that radical. They are inverse operations. They undo each other. 10 squared is not 20. 100. Here you just have 6x. So divide by 6. You can write it as 50/3. It's a repeating decimal, or 16 2/3, I think. Does that make sense? Yep. Okay, that's basically one of the big theorems we learned. The other theorem we learned was called the leg theorem. This one I called the altitude. This one was the leg. And the legs of a right triangle, so that's obviously these ones that form the right angle. Those are my legs. The leg is the geometric mean of the entire hypotenuse and the side. Let me use a different color. The whole hypotenuse and the piece of the hypotenuse that it touches. So here they're showing me this little segment's 4. This side's 24. So what would the whole hypotenuse be? 28. Yep, 28. Okay, so the leg theorem says that the leg is the geometric mean of the whole hypotenuse, 28, and the piece that it touches, 4. That is 112, which that is 16 times 7. And remember, those folks, I just kind of get by taking my calculator and taking the radicand, the number underneath the radical, 112, and start dividing it by perfect squares until I find one that it's divisible by, and then I can break it up. Okay. So last one similar where This time my unknown is the whole hypotenuse, but I can see I'm given this little segment that touches this leg, and I'm actually given this leg. So we're going to use that same relationship, or that same theorem, that the leg is the geometric mean of the whole hypotenuse, which is x, and the segment it touches. So instead of writing that as x times 18, I'm going to do 18x. And then similar to number 4, to solve this, I would have to square both sides. And we get 32 for x for that one. Okay, now do we remember it? You guys just all went home that Friday after spring break and cranked out your 8-1 worksheet and your 8-1 book assignment, so you didn't have to worry about geometry over all of spring break, right? That's why it's been so long. I knew it. Your 8-1 book's due tomorrow, so if you haven't started it, you'll get some good practice with that stuff. Okay. So 8.2 is our good friend, the Pythagorean theorem, which I know you guys already know how to use it, but there are some like more applications that we're talking about today with the Pythag theorem that you haven't learned before, so it's kind of fun. And also, I know some of the triangles from 8.1 you could solve with Pythag, which is like fine. But when you're doing your 8.1 homework, like practice using the geometric means. Okay. All right, our good old Pythagorean theorem. This is just like a classic. You ever see like a math T-shirt? I have a couple, or like like math mugs too. One was like, I'm a math teacher. Of course, I have problems. It has a bunch of math problems on it. But usually, like the Pythagorean theorem is like always on those. It's so classic. One of the top 5 most popular. And it can only be applied to a right triangle. So if we know the triangle is a right triangle, then my 2 legs, which we often use, a squared and b squared. The square, both my legs, oh my gosh, I've dropped so many markers today. Not good, not good. That sum is equal to the hypotenuse squared, and obviously the hypotenuse is the one across from the right angle. Legs, hypotenuse. Okay, so as a review, we know how to do that. Let's take a look at a couple problems of using the Pythagorean theorem. Just be careful, even if the triangle is orientated differently, like here, 4 is still a leg, 7 is still a leg, because the side across from the 90 is my hypotenuse. So if I want to set up Pythag here, I would do 4 squared, and I like to put parentheses around. You'll see why in the next problem. 4 squared plus 7 squared, those are my 2 legs squared. Their sum is equal to the hypotenuse squared. Good old Pythag. So we would do the math. 4 squared plus 7 squared is 65. Oh, here's a good look at, before we had equations with the square roots and we squared both sides to get rid of the square roots. Now to get rid of the squaring, we square root both sides. Because that gets rid of that layer. So you get x is the square root of 65. That radical can't be simplified. There's no perfect squares like 1 to 65. I feel like some on the homework might ask you to like round to the nearest tenth or something. So if they ask you to do that, just go ahead and use your calculator and square root 65. It's like 8.1. And I kind of like doing this anyways, because then you can check if your answer makes sense. Because we know the hypotenuse should be what in comparison to the legs? Greater than or bigger. Yep, this should be your biggest side. Is it? Yes. Okay, so you can always kind of check if your answer makes sense. This one's a little different because this time I know my hypotenuse is 12, and I don't know one of the legs. So I'd set it up the same way. X squared plus 8 squared, my 2 legs squared, equals my hypotenuse squared. All right, so that'd give me 64, 144. Subtract that over, we get 80. Square root both sides. Okay, I know 16 goes into 80, so we can simplify that radical. 4 root 5, or approximately 8.9 is what I got for that decimal. Just check that, make sure it's not longer than your hypotenuse, and it's not. All this still my longest side. All right, so there's just a good little refresher over using Pythag. There's some like that on your homework, pretty straightforward. Questions? Oh my gosh, I love this next one. This is gonna be so fun. Okay. This one is very similar. We can use Pythag because it's a right triangle. Just I have a couple of variables. That's okay. Let's still set this up like we normally would. So I have my leg of 8 squared. Here's where I like to use parentheses. If I have something like this, x minus 4 squared, that entire length is being squared, so you have to write that in parentheses. I don't care too much about the 8, but something like this you have to. And that equals my hypotenuse squared, which is x. Okay, 8 squared is 64. I'm going to give you guys like 1 minute to see if you can figure out what this is. I think I had 2 people in 7th hour do this correctly. Okay, stopwatch. I'll give you, how about this? 1 minute to try it on your own, and then 1 minute to talk about it with a partner. How fun. If I can find the dang stopwatch on my Apple Watch. I get it confused with the timer. They look the same. That's timer. Okay, ready? Go. 1 minute. See if you can figure out what x minus 4 squared is. I'm telling you right now, it's not x squared minus 16, and it's not x squared plus 16. It's not either of those. Exponents don't distribute. Me too. But I'm afraid I have bushtail. Ready to reduce it geometry.
I'm sure I passed it.
I'm sure what?
I'm pretty sure I passed it.
You did for sure. Is it a competition now? Okay.
Yeah, sure.
All right, that's a minute. So now you have a minute to talk about it with someone else, see if you can figure it out. Go. Someone next to you. Oh no! I feel like I heard you say the right.
Yeah.
4. Don't worry. I feel smart now. You should.
Yeah, because it was.
Wow, guys, this is a big
16 times 16.
outside.
130.
X is not 0. Anybody else get it? Yeah, good.
I forgot about
I'm not even close. I see 2. Okay, right idea, Libby. Right idea. I see 2.5 people do it correctly. Yeah, you're the half. You guys are making how? Oh, do you have to? Yes. Oh my gosh. Okay, minutes up. Let me ask you this question. I think some of you will see it. How do you rewrite 8 squared as a multiplication problem? Okay, that's what 8 squared is telling you. Take this number times itself how many times? 2. Right? So it's 8 times 8. So this is saying take x minus 4 times itself how many times? Twice. So this is saying do this. X minus 4 times itself twice. Exponents don't distribute. If you thought this, that's like the number one mistake people do. Even, I don't know if I told you guys, like when I was in college, I used to like tutor math. That was like my job. Like I made money to do math. It was awesome. And even college kids, I'm telling you, would do this. They're like, oh, that's the same as x squared. No. Exponents don't distribute. When you have a product, something like this, which again, think of what this is saying. This is saying take 4x times itself twice. Then yes, you need to square the 4 and square the x. But when you have a sum or a difference, you can't just like distribute it. You gotta write it out. And a method to do this is I heard FOIL, but really, I don't love the word FOIL, but if it helps you remember how to do it, that's great. Because FOIL only works when you have a binomial times a binomial. That just means 2 terms times 2 terms. So really what you're just doing is distributing. All right, so to multiply this out, I have to take x times x minus 4. So that's going to give me x squared minus 4x. You got to distribute the x. Oh my gosh. And then you got to distribute the negative 4. So negative 4x, negative 4 times negative 4 is 16. And when we add these all together, my like terms here, you'll see this is not the same as x squared minus 16, right? It's not the same as x squared minus 16. It's x squared minus 8 plus 16. All right, so that's how you multiply that out. Good review over some algebra. All right, I still have this 64, and I still have this x squared. So yeah, we could add the 16 and the 64 together. You can do that if you want. But as I'm kind of thinking ahead to solving this, I'm thinking I got to group all my variables together. And what happens with like these x squares? Like let's say I move this one over to this side. They cancel out. Yep, so you end up getting 0. So don't worry, we don't have to factor. So on this side I have negative 8x plus 80. What do I have on the right-hand side of my equation? 0 or 1? 0. Good. Yep, good. 0. Nothing. Not x squared. 0. Okay, so to solve this, I'd probably add over the 8x. Divide by 8. X is 10. You could check your answer by plugging them back in, using Pythag, and it will work. So just as like a little side note, you don't have to write this down, but when you get to Algebra 2 next year, you guys will start multiplying out like trinomials, which mean like 3 terms times maybe another trinomial. Maybe something like this. And really, all you got to do is distribute. You just got to distribute this guy, distribute this one, and distribute that one. Fun stuff. So, careful with that. Okay. Just Pythag. Just maybe a little bit more challenging application. Here's something you guys haven't seen before. Something called a Pythagorean triple. Or have you seen that before? Someone told me no. Sound familiar to anyone? So it's basically like a set of 3 whole numbers. A set of 3 whole numbers. Whole numbers are positive counting numbers, so like no fractions, no decimals. That when I plug them in with like Pythag, they work. Or if I take like my 2 legs squared, my hypotenuse squared is also like a whole number. So I might get like the square root of 25. Okay, it's 5. It's not something like the square root of 61. That wouldn't be a whole number. So a set of 3 whole numbers that work in Pythag is a way to think of it. Okay, so here are common ones that for now you can like use your notes. I don't expect you to memorize this, but use your notes to like recognize these Pythagorean triples. So if the directions say, there's a couple like this on your homework, use a Pythagorean triple to find x. They don't want you to use the Pythagorean theorem. They want you to use this Pythagorean triple, and really it's just like a pattern recognition. Okay, So here in the gray boxes, these are all my Pythagorean triples. Basically, if my two legs are 3 and 4, 3 squared plus 4 squared is 25, so the hypotenuse is going to be 5. If the leg is 5 and 12, the hypotenuse is going to be 13, etc. with the other two. So we talked about last chapter like similar triangles and having like scale factors. So if we were to look at, say we're to double all these sides, like here, 6, 8, 10, that's still a Pythagorean triple of the family 3, 4, and 5. I just doubled all the sides. I tripled all the sides. So basically you can have any factor times that ratio, that 3, 4, 5 ratio, and that would be a Pythagorean triple. Okay, so I could times them all by 10. So if I had 30, 40, and 50, that would still be a Pythagorean triple. Okay, that's what that's saying with, so same here, double, triple, any number of times, etc. So this one is actually on the chart, but here's how you would use Pythagorean triple to find x. It's arguably a little bit more work than just doing Pythag, in all honesty, but it's just another way to look at it and recognize some patterns. So the first thing you got to do is you want to find a common factor with the sides that are given to you. So the sides that are given to you are 39 and 36. So I want to find a common factor of 39 and 36. Okay. Anybody got a common factor? So factors are numbers that go into of 39 and 36. 3. 3 goes into both of those. They're both divisible by 3. All right, let's do this math. So 39 divided by 3 is 12. 36 divided by 3 is 13. So then you go to your list and you try to find one of the Pythagorean triples that has 12 and 13. And I'm like, ooh, this one right here. And especially because 13, that 39 one, was my hypotenuse. And yeah, it's listed right here, so you can tell what it is. Yes, question?
You got your answers.
Oh, thank you. 13 and 12. Good catch, Ben. Thank you. Okay, 39. That's my hypotenuse one. Phew. So I thought you were going to say, like, it's right there. So then you find your, basically like your Pythagorean triple, like families, I like to call it. So this one, after I like broke it down a little bit, I see it looks like a pattern of 5, 12, and 13, right? Where one of my legs is a multiple of 12, and my hypotenuse is a multiple of 13. So I'm going to write down that Pythagorean triple. This is the family it's from. 5, 12, 13. You can write it as a ratio if you want. You don't have to. And I know my scale factor here, I'm just going to put the scale, is we're timesing everything by 3. However you want to write that. Okay, so this leg was 12 times 3, 36. This hypotenuse was 13 times 3, 39. So to find the other side, I'm going to take 5 times that scale of 3. And so my other side is going to be 15. And again, you could see that pair right there because they're showing you double and triples of each. But that's how you could do it. And again, I know it's probably like, I think it would be way easier. I agree. But use some pattern recognition. It's good to try to solve something 2 different ways. So find the common factor. Find the Pythagorean triple family. You can reference this chart. Figure out the scale to find the missing side. Okay, that's what I would need to see for your work on those. All right, last thing we want to talk about. The converse of the Pythagorean theorem. So remember, converse, we just flip-flop the hypothesis and conclusion. So in regular Pythag theorem, the hypothesis, I keep wanting to say hypotenuse, the hypothesis is if it's a right triangle, and the conclusion is then a squared plus b squared is c squared. So if we flip-flop those, if a squared plus b squared equals c squared, then what can we conclude? It's a right triangle. Yep. Okay. If it doesn't equal the hypotenuse squared, then it's not a right triangle. And we can actually classify what type of triangle it is based on the relationship of the two, I don't want to call them legs, because technically in a triangle like this, A and B, the two smaller sides aren't legs, because it's not a right triangle, but the two smaller sides, if they're the square of their sums, or the sum of their squares, we're going to say it, is larger than the hypotenuse or less than the hypotenuse, then we can figure out if it's either an acute or an obtuse triangle, okay? I don't love the order they did this, because usually with Pythag, we would do like a squared plus b squared equals c squared. So I'm going to order it like this. So the two smaller sides squared, if their sum is greater than the largest side squared, so picture this. If these two, if I square them and add them together, and this one is smaller, this one is like small, then that means this angle that's across from is small, and it's going to be in a acute triangle. All right, similarly, if the two smaller sides squared, well, if it's equal to c squared, then it's a right triangle. If it's less than, if that third side squared is large, big, then think it has to be across from a big angle, an angle bigger than 90 degrees. We call those obtuse angles, so then it's an obtuse triangle. Okay, so we're going to practice 4 of these problems. What time do we get out of here? 21? Yeah, 6 minutes. Time flies when you're having fun, huh? Okay. So the directions here say, determine whether the set of numbers are even a triangle. If they are a triangle, classify that triangle as acute, right, or obtuse. So, if you remember from chapter 5, if 3 sides are a triangle, the sum of any 2 sides always has to be greater than the third side, right? Remember that? I made you check all 3 possibilities. For now, if you're testing if it's a triangle, I'm okay with, since we already kind of went through that in chapter 5, I'm okay with you just taking the smaller 2 sides and making sure the sum of the smaller 2 sides is greater than the largest side, okay? Because then obviously from there, the other one should hold true. So 9 plus 12 is 21. Is greater than 15. Okay, so we know this is a triangle. So now to determine if it's right, acute, or obtuse, we're going to kind of do like a little version of the Pythag. We're going to take the 2 smaller squared and add them together. And then instead of the equal sign for Pythag, put a little question mark here. What's that relationship with the largest side being squared, which could be our hypotenuse if it's a right triangle, but let's look at this relationship. All right, so quick do this in your calculator. 9 squared plus 12 squared is 225. 15 squared is 225. Obviously, those values are equal. Pythag whole. So what kind of triangle is this? Right triangle. And this is your justification, folks. You showing your work right here. That's your justification. What's the relationship? They're the same. All right, next one. First check, is it a triangle? Well, let's make sure that the sum of the 2 smaller sides is greater than the third side. And here it's not. So it's not even a triangle. So you don't need to check Pythag. Save yourself some work. It's not even a triangle, so you don't need to go any further. Decimals. Does that freak you out? Good. All right, let's check if this one's a triangle. I'm on C. Is the sum of my 2 smaller sides, is it greater than the third side? It is. So yes, this one's a triangle. What type? I'm going to do my little version of Python. I'm going to take my two smaller ones squared, add them together. Question mark, what's the relationship with the third side squared? Don't put equal because we don't know that for sure. We're testing it. All right, I did this quick math for you. This over here is 6.4925, and 2.5 squared is 6.25. Okay, not to like rush you, but just to save time. Obviously, these aren't equal, so Python doesn't hold. So what's the relationship with this? Is 2.4925, is that greater or less than 6.25? Greater. So that means that third side is small. So since that's small, that means it's going to be a small angle, meaning it's an acute triangle. If that third side is small. Okay, last one. Is this a triangle? Is 7 plus 15 greater than 21? You betcha. 22 is greater than 21. Yes, it's a triangle. Hold on, don't pack up yet. That's rude. So let's check Pythag. Is 7 squared plus 15 squared, is it equal to 21 squared? Is it greater? Is it less than? We don't know. That's what we're testing out. It's a big old question. All right. 49 plus 15 squared. 274. 21 squared is 441. This time, my two sides squared added together, that's smaller than that third side, so that means that third side is big. So it looks kind of something like this, where that third side's really big, which means the angle across from it's going to be really big. So this is an obtuse triangle. Okay, that's how you test that. I do want to pass out the worksheet to you. Quick. The 8-cube worksheet.